I'll get out of the way. In this example, you're asked to find a basis for both the row space and the column space of this matrix A. So remember that the row space of a matrix is the collection of all linear combinations of the rows of a matrix. So if we're trying to find a basis for the row space of A, remember that the two criteria for a set of vectors to be a basis is that they span the set. So if we just simply took the rows of A and made that our set, vector 1, vector 2, vector 3, then that would span the row space by definition. So the question really is how do we form an independent set out of the rows here? Now, there's another theorem that I just mentioned in the notes that says elementary row operations do not change the row space of a matrix. So that's saying if I take a matrix A and I do whatever row operations I want, whichever elementary row operations I want, and turn it into a new matrix, let's say B, then the row space of the original matrix A is equal to the row space of B. So if I find a basis for the row space of this matrix, or if I find a basis for the row space of this new matrix, imaginary matrix over here, well, since those sets, row space of A equals row space of B, it would be a basis for either one. Okay, so what we need to do first is row reduce this matrix. So a few row operations. I'm going to try to go through this part fairly quickly because row operations are something you've been doing forever. So if you take -3 times first row plus the second row, that'll zero out this entry here. So -3 times row 1 plus row 2 will give us, let's see, 0, 2, 2, -2. And then I'll leave this row as it is for now. We could then do 1/2 times row 2. So that'll give me 1, 0, 1, 1, 0, 1, 1, -1. And then, I'm cheating a little bit doing 2 in one, kind of one step here, but after that, let's say we did -4 times row 2 and added that to row 3. -2 times this row 2. Sorry, -4 times that row 2. So -4 plus 4, so 0. -4 plus 4 here, so 0. +4, because we'll have -4 times this, so +4 plus -4, so 0. And then there is the reduced echelon form of A. Turns out is this matrix here. I'm just copying it so I can erase this space here and use it to explain our next steps. Okay, so there's your reduced form. Where's my eraser? Okay, so if we want a basis for the row space of the original matrix A, we can just use the rows of this reduced form here as our basis, the non-zero rows. So for the row space of a matrix A, or I'm sorry, for a basis of the row space of a matrix A, we can use the, or let's just say non-zero rows of either, just regular REF form or RREF. Oops. REF. Okay. So use the non-zero rows of one of those matrices. So in this case, our basis for the row space of A is going to be these two vectors here. Now, what about a basis for the column space? Let's get rid of this circle. I'll just rewrite it. Okay, so what did we have? 1, 0, 1, 1, 0. What was this? This ended up being -3, 2. Yeah. So 1, 1, -1. Okay. Okay, so our basis for the row space of A in this case is the collection 1, 0, 1, 1 and 0, 1, 1, negative 1. There you go. And the dimension, while we're at it, of the row space of A is 2, because we have 2 entries there. Now, what about a basis for the column space of A? So if you think back a couple of sections, you can find a basis for the column space of a matrix by looking at the pivots in your reduced form and using the corresponding columns of the original matrix. So if I have a pivot in column 1 here, then column 1 of the original matrix is going to be one of my basis vectors. Pivot in column 2, so column 2 of the original matrix is going to be another one of my basis vectors. And so this is a basis for the column space of A. This also contains 2 vectors. And in fact, dimension of the row space is always going to match the dimension of the column space. So in this case, 2. But these guys will always be equal because they're both coming from where the pivots are. So for row space, we use, it's non-zero rows of the reduced form, but so it's the pivot rows. That's our basis for the row space. We use the pivot rows of REF of A. And then for a basis for the column space, we use the pivot columns in the original matrix. But so either way, it's corresponding to the pivots. So it's always true, in fact, that, can you see if I write down here? Yeah. The dimension of the row space of A will equal the dimension of the column space of A. Because either way, like I said, it's just going to be equal to the number of pivot columns. And so we call this value the rank of A. But so the rank of A, another way of thinking of it is it's equal to the number of pivot columns or rows, whichever way you want to look at it. Or let's just say number of pivots.